Okay, good. All right. So I want to talk about an alternate source of carbon other than meteorites we've been talking about today. And working on these for about 20 years, you can see we've recruited a lot of collaborators. And I also say that I'm part of, I'm a minion on David Kring's survey empire here in Houston. So I'll just hit it right at the top. So let's go on. This is actually a 30-minute talk. I've condensed down to 15 minutes, so I'm going to go pretty fast. So this starts 20 years ago when these two meteorites fell. They're H5 ordinary chondrites, and they contain halite. The halite was dated several ways to be 4.5 billion years old, plus or minus large error bars. And the halite also contains aqueous fluid inclusions, which is really neat. And you see a bubble moving around here with the arrow points. So there's actually liquid water in there right now. So it was trapped at room temperature on some object. It wasn't trapped on the H. chondrite parent body. It's material that formed somewhere else in the outer solar system and landed on the H. chondrite parent body, relatively intact, which is almost a miracle. Go on. Okay, so years later, Ito-san and Yamamoto-san measured oxygen and hydrogen isotopes of pre-selected fluid inclusions in these halites, and they found that the analyses could be explained by a mixture of carbonaceous chondrite water and cometary coma water, if that's what you want to do. Basically, it was nothing we've seen before. These analyses, these are individual analyses, individual fluid inclusions, it's a miracle these are measured. It's really hard to do this, but the reason I'm talking about it is because in the course of their analyses, they recognized that there were small solid inclusions in the halite in addition to the aqueous fluid inclusions. And this is also found by Mark Friese and Steele at the same time, using Raman. And so we embarked on a study of these inclusions in the halite. Here's one shown here. And Mark found that most of these were, in fact, organic dominated or totally organic grains. And so a small part of the story is digging out these little guys, analyzing them one at a time, which is taking a really long time to see what they are. The cool thing is the fact that water survived in these halite samples means that they have not been heated in 4.5 billion years. Had they been heated at all, water would have migrated out of the halite. So the organics that are trapped in the halite have also been sitting here unheated for the entirety of the solar system, pretty much. So these could be the least processed organics we have in any astromaterial. So I'll move on. So Mark and others at Queenie Chan have been doing Raman of individual grains of organics and silicate oxides, whatever, in these halites. Here's one that this is macromagnetic carbon for the second time today. Green is pyroxene, blue is olivine grains here in this one little aggregate here. These are the size of micrometeorites, basically, in the halite. And wherever you go, you find different things. This is a diamond grain mixed with graphitic macromagnetic carbon and also carbonates. That was shown by this Raman spectrum here. Here's the spectrum of the grain in the halite, and here's a spectrum of diamond crystal in uralite, and pretty characteristic Raman spectrum. So this is a pretty unusual mixture of minerals in the halite. Again, I'm not an organic chemist, so I'm going to breeze through a lot of these slides. But I just want to give you an idea that these are very organic-rich samples, and analyses are very, very difficult to do on these tiny things, but they're gradually revealing what they are. And there's quite a mixture of organic materials in here, so I'm going pretty fast through this. Here's Mark found methyl chloride in one grain. This is probably methane-bearing organic grain where the gas is diffused out of the grain and then combined with chlorine from the halite to make methyl chloride. That's probably how it formed. The cool thing is that similar material was seen geysering out of Enceladus. The geysers of Enceladus, the sea spacecraft passed through these geysers and they detected some kind of salt, not necessarily halite, organics, and methane. I think also silica grains as well. Very similar to what we're seeing in these halites. I'm going pretty fast. So Mark dissolved one of these, I think Monahan's halite grains here, about a millimeter-sized grain, and got all these little occlusions out. The biggest one's about 300 microns in size. Each of these is about the size of a micrometeorite or a large IDP, and they're all quite different. So it's gradual work to figure out what these are. Yoko Keibokawa, who's at Yokohama University, so Yokohama. She's been doing FTIR and carbon zanes on these grains as we've been fibbing them out one at a time. And here's just an example of what she found in one grain. This is a fibbed out organic grain from halite, blown up here. And then this little circled area was analyzed by carbon zanes, and she saw a wide variety of organics in a small area here. This is just a few microns in size. So an amazing variety of organics that has survived for a really long time, including either diamond or carbonyl here. It's kind of strange, but very interesting. Again, I'm going pretty fast. A lot of it's published. A lot of this is not published. So if you have any questions about what's out there in the publication world, just ask me and I'll tell you. But that last one was published. This is just a summary of the mineralogy we've seen to date in the solid grains in these halites. As you can see, it's an amazingly wide range of materials. Organics are the bulk of the material. But the important thing is that these are not from the H. chondrite parent body. These are material that landed on the H. chondrite in the regolith, or it was incorporated into the H. chondrite after metabolism ceased, and these halites came from somewhere else. And we're thinking that the halites formed from a hydrovolcanism on some object, and that as the water passed out of the object, it entrained bits of dust, solid dust and organics from the mantle of that object. And then when it cooled and dried, it made halite with these little trapped organics and other silicates and other materials inside. So we're sampling the interior of some large water-bearing parent body in the early solar system. One of the things Queenie Chan did at JSC, working with Aaron Burton, was to see if she could extract amino acids from grains of halite. And I'll just say that she went to great lengths to ensure there was no contamination in the halite samples. We had a sample that we've kept at nitrogen for 20 years. We did the work in a class 10 clean room. We cauterized all the tools. We actually carefully chipped into the sample and exposed brand new halite crystals from inside the sample. The halite crystals were still blue or purple, which means they haven't been altered on the Earth. And what they found, this was published in Science Advances earlier this year, is a wide variety of organics in the halite. So this is totally solid grains in the halite, as well as small organic molecules dispersed in the halite itself, but a really wide variety of things. And they even successfully managed to detect some amino acids in the halite. So the purple dots are excesses of amino acids over the background in the meteorite. So where there's purple dots higher than the white or black spots, that's amino acids that are at higher level than you're seeing in the background, essentially. It's pretty amazing that these survived for so long. And this is really hard to do. Anyway, I'll go on. This is published in Science Advances this year. So we've proposed that perhaps these halites came from, this got clutched up, but proposed from Ceres, perhaps. And there's dynamical reasons for saying this could have happened. But it's also possible that it's not from Ceres, but something a lot like Ceres. And we're suggesting possibly something from further out in the solar system, TNO, which would be looking like a P or D asteroid after a giant planet migration. So what I'm suggesting is that these organics came into the inner solar system, smashed into the an S-class asteroid, and came from somewhere further out. Maybe one of these TNOs, which are pushed into the inner solar system during giant planet migration. But irrespective of whatever model, this is definitely material from the outer solar system, and we'll see why. Moving on. Well, it turns out that also in this same meteorite with the halite, ZAG, there's a class, C. chondrite class. It's about the size of your fingernail. It's pretty cool. We've been looking at this for a while. Here's a thin section, actually a polished section of a bit of this C. chondrite class. It's mostly phyllosilicate, serpentine. A lot like what you'd see in a CI chondrite, but it's not a CI chondrite. The bright things are magnetite and sulfides. This is a really huge carbonate cluster here, which is datable. Working on that right now. You can date the timing of the aqueous alteration. But also in here, and by the way, we have bulk oxygen analysis on this class. Here's, I won't explain the oxygen isotope plot here, ordinary chondrites. They're down here, other things. This is terrestrial fractionation line. This is where the CI chondrites plot, and here's where this ZAG class plots. It's clearly not a CI chondrite. It's something very different. This is done by both Bob Clayton, the late Bob Clayton, and Tosh Maeda, and recently by Richard Greenwood, and they get the same results. And there's also a big delta D here, which I'll describe here in a minute, which is also a very important part of the story. There's halite in this class. So this carbonaceous chondrite class pretty clearly arrived at the S-class asteroid with the halite, because it's halite in the class. So they were formed on the same parent body, you think. So this is definitely the mantle of whatever object was hydrovolcanically active. This is a close look at the carbonate. This is a really huge carbonate grain, and it's we'll date it, I think, next year in the University of Hawaii. Cool thing here is that also in this class are lots of small organic grains. Whoa, it's hiding away. So the little numbers here correlate to little grains of organics that have been slowly sifting out, analyzing by Raman, FTIR, and Zanes. There's organic nanoglobules in this class. Here's one here. And here's one of Yoko's carbon-Zane spectra of various areas in another one of these organic grains from this class. Again, a very wide range of organics in very small areas. So a real mixture of different organics surviving from the early solar system. This is one of these grains. This is the BSC image of the ZAG class here. And this little black thing right there, that's this organic grain. You see, it's pretty small. Here's a 100 micron scale bar down here. And here it is fibbed out. This is the organic area. And here are results of nanosims analyses by Moto, Ito, and Yoko of portions of this fibbed out organic. The cool thing here is, here's a map of, this is nitrogen 15, which is a heavy neutron-rich isotope of nitrogen. And this is deuterium, the neutron-rich isotope of hydrogen. And you see correlated excesses of heavy hydrogen and heavy nitrogen in different spots in this class, which is very unusual, and those suggest very cold formation temperatures. Again, outer solar system stuff. And you've seen this before. I won't dwell on it. It's just that there are ways of getting outer solar system material in and smashing into the S-class asteroids. And that's what happened here. Bits of material, it could have happened here. Bits of material from out here was brought in, smashed into the S-class asteroids, and surviving relatively unheated, unshocked bits of these have survived here and there in these ordinary chondrites. So here's a recent thing you may have seen at LPSC. People are looking at nitrogen-rich isotopes of titanium, chrome, nickel, and molybdenum. When you plot those against the heavy oxygen, here versus here, this is a plot just of one of these. This is chrome-54 excesses. What you see is that meteorites seem to follow one of two trends. Almost all the meteorites are here, but all the C chondrites are over here, which is very interesting. And if you look, you notice, based on Dan's talk before, you'll see this like progression of wetter and wetter, more carbon-rich as you go in this direction here. And so one interpretation is that Jupiter was here, basically preventing materials from mixing back and forth. And there isn't time to talk about this in this talk right now, but I think you probably know the details of this. Talk to Bill Bakke about this if you want to. So the idea is these could be outer solar system materials formed out beyond Jupiter that could be where all C chondrites originated. And we're wondering, could there be materials that are out here, even more water and organic rich, maybe from even further out in the solar nebula? And here's where this ZAG class plots. Oh, I lost my little pointer. Where did it go? Yeah. Okay. Here. So it's even more extremely water and organic rich than CI chondrites. And if you saw Christina Gibrich's talk at LPSC or Kinzu Yen's talk at LPSC, you know there are actually other things up here as well that are mineralogically very, very similar. So these little bits of things are accumulating that look to be even more organic and water rich than CI chondrites, and maybe are more likely surviving samples of early solar system organics than in, say, CI chondrites. So these are pretty common, actually, it turns out. Several classes have been reported in all kinds of ordinary chondrites. Scuba, here's one in the Scuba H5 chondrite reported many years ago. You should see very little work in the last 20 years. We'll be working on it this year. I think I bought this on eBay. If you go on eBay, you can buy all kinds of cool stuff, including ordinary chondrites. It's an H5 chondrite with C chondrite class in it. This one looks identical to the ZAG class. So we've done almost no work on it so far. It's pretty big, so we'll get a lot of analyses on it. This is a class that was in the Carbonaceous H4, H5 chondrite, given to us by Jason Utas, which has veins of organics in it. This is something that Queenie Chen talked about at LPSC. I haven't seen this before. It's pretty cool. And again, mineralogically, it's identical to these other materials here. And by the way, if you don't know Carbonaceous, it's the one that made the smelly crater in Peru about 10 years ago, the one that got people really sick because it happened to land over an area which had arsenic-rich groundwater. So it's a kind of a dreaded meteorite. Now, we mentioned vestoids here. As you all know very well, there are lots and lots of C chondrite class in most tauroidites, not all of them, even in some eukaryotes, even at least one diogenite. And the largest of these, as we know, are always very similar to CM chondrites. But the real tiny ones here haven't been studied very much in the last 20 years. We looked at them about 20 years ago and found that half of them are more like CI chondrite material, or in other words, a lot like these classes we're seeing in ZAG. These haven't been studied at all, I think, in the last 20 years. We were looking at the CM chondrite class. These little ones here are maybe more interesting. And here's a blow up one of these from a eukaryote, which is, again, mineralogically identical to the ZAG class. Lots of magnetite and sulfide, mostly phyllosilicates, big carbonates. It's the same thing. No study of all the organics in these yet. So I'm winding up here. So our idea is that these hydrous class are probably identical to P and D class asteroid material. And by the way, I can go back here for a second. Excuse me, forgot to mention something kind of important here. If you're wondering where Tagish Lake plots on this diagram, whoa. Where Tagish Lake plots, it's actually down here. And so if Tagish Lake is from a D-class asteroid, D-class asteroids are not what we think. Because Tagish Lake plots, this is like published about 10 years ago, Tagish Lake plots down here. So that's a very interesting thing to think about. I'll go on. My final talk again, sorry. So our idea is that these little class, which are in ordinary chondrites and other kinds of meteorites, including maybe also the ATDs, are perhaps better samples of P and D class asteroid material than any meteorites, including probably Tagish Lake. We're going to try to date the carbonates in these in the coming couple of years. We got a PhD student in Hawaii who'll be working on that. They've been struggling over standards. You finally solved that problem for calcite at least. And I haven't mentioned it, but there are actually associated very carbon-rich, actually graphite-rich and hydrous class in these same meteorites, which are shock melt materials, which could be highly shocked analogs, these same things that came in at a higher velocity and got melted and shocked during impact. And they're rich in carbon, lots of graphite. Here's an example shown here. Here's these anhydrous class in ordinary chondrite, this is a close-up view of BSC view, and these black lines here are graphite, acicular graphite crystals. They're not plates, they're actually little pencils of graphite. And there's up to 3 wafer% carbon in some of these class in graphite. These are impacts of very carbon-rich material into these same S-class asteroids. So we're going to try to date these by argon dating to find out if these are really the recent impacts into the SS-class asteroids, or if they could in fact be from earlier epoch and source of history, perhaps even dating the time of giant planet migration, if you believe that model. So I'll just stop there. Thank you.
Thank you, yeah. Jeff. Questions from elsewhere.
Yeah,
I
see Jeff's question. And Jeff's question, what's the aromatic aliphatic ratio in the Monahan STIP section? I don't know, but if you ask Yoko Kabukawa, she can tell you that. So if you don't know Yoko, just send me an email and I'll put you in touch with her. Or Queenie Stanton.
Hey, other?
Oh, hey, Mike, this is Bill Bach.
I recognize you.
I'm a co-author on some of this, so I can't.
Yeah.
So I can't ask too many questions, but I have a more general question. So I've talked to Matthew Ginnell, and I remember like really old papers from back in the 70s where they were talking about like these dark inclusions all through various meteorite classes. Are dark inclusions the same thing we're talking about here?
These are some of the dark inclusions are these. There are all kinds of dark inclusions. So there like there's a lot of dark inclusions in Allende, for example, in CD chondrites that are actually metamorphosed CD chondrite material. No relation to this whatsoever. So some of them are C chondrite stuff like this. Some of them are CM chondrite material. Some of them are toxic things. But you talk to Matt. He's an interesting person.
I like to talk to Matt. No, he said he's collected papers on this over the years, and I've been super interested in it since I saw like a George Wetherell paper that talked about this kind of stuff. But I've never seen many people follow up on it. So
come to this workshop in June in Paris.
Paris in June?
Yes.
That'll be really hard.
Yeah, Matt's long held that orgate comes from a comet too. So maybe he's right. But there's definitely there's obviously a complete continuum between asteroids and comets, so maybe it's not an important thing to worry about. But Matt and his student Giacomo Briani were looking at these little class in the HEDs years ago and recognizing that they were not CI chondrite material, that they were in fact something different. More like they call them more like micrometeorites, but they were something totally different. We need to go back and look at those again. They've been ignored too much.
In work I did with Alan Rubin, Alan was claiming that some of the class in H chondrites and HED and eucrites, I think were more like CM chondrites. So I think there's got to be a mix.
The biggest ones always are. But the small ones contain a mixture of that plus these other weird things, which years ago we were at a loss to say whether they were, we call them CR or CI chondrite-like. But we need to go back and do some isotope analyses on these to see what they really are. No one's done that. And should.
Hey, Mike, you have a question, another question from Diane Wooden on, do you see a relationship between class and cometary material?
Maybe. Yeah, we're working on that now. So actually, there's a grad student in Hawaii, Dave Wang, worked on built 2 grains, who's going to be taking over a lot of this work from me. So talk to Dave Frank about this. But yeah, we're obviously thinking about the connections between built 2 samples and these little class. It's an example of where we have a lot of analyses of one type from one type of material, and in these class you have other kinds of analyses. We haven't got the same data set for both kinds of analyses. We've got to do that.
Okay.
But if you go on eBay, you can find one of these tonight. If you look, you can buy it, own it yourself. You can have a little P or D class asteroid in your own collection.
Aw.
Yeah, I know one right now. Yeah.
Other questions?
Gonna make a profit.
Yeah, Diane needs your coaching on getting some of those.
From eBay?
Okay, then
no problem.
I'll move on to Sabrina Goodrich on space